Hello! In this video, we are going to prove the following theorem. Every non-empty subset of positive integers has a smallest element. Now, this fact is often referred to as the well-ordered principle. And in proving this theorem, we are going to be using the following notation. For each integer n greater than or equal to 0, we let in be the set of positive integers I, such that I is less than or equal to n. For example, I0 is empty, I1 consists only of 1, I2 consists only of 1 and 2, and so on. Now, let's be really clear about what we mean by smallest element. Given that S is a subset of the positive integers, and M is a positive integer, then for M to be the smallest element of S, we need the following two conditions to be met. We need M to be an element of S, and we need every element of S to be greater than or equal to M. Okay, so now let's get into proving this theorem. Now the idea for the proof is we're first going to prove by mathematical induction, for all integers n greater than or equal to 0, we have that every non-empty subset of In has a smallest element. So let's start with the base case. Now in the base case, we're trying to show that every non-empty subset of I0 has a smallest element. Now we know that I0 is empty. And since I0 is empty, it follows that every subset of I0 is empty as well. Or in other words, there is no subset of I0 that is non-empty. So it is vacuously true that every non-empty subset of I0 has a smallest element. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary integer n greater than or equal to 0, and we assume that every non-empty subset of In has a smallest element. And the whole goal of the induction step is to show that every non-empty subset of In plus 1 has a smallest element. So to prove that, let's give ourselves an arbitrary non-empty subset of In plus 1. I'll call it S. From here, the whole goal is to show that S has a smallest element. And to show that, we're going to split this up into two cases. Either 1 is an element of S, or 1 is not an element of S. And in either case, we're going to show that S has a smallest element. Let's first consider the case 1 is an element of S. The claim is, if 1 is an element of S, then 1 is the smallest element of S. So to show that, well, according to the definition of smallest element, we're taking n to be 1. Well, in that case, we need to verify that 1 is an element of S, and every element of S is greater than or equal to 1. Well, we know that 1 is an element of S. That's what we have here. So this first condition is met. But now, we would like to show that every element of S is greater than or equal to 1. And to show that, well, if we considered an arbitrary element of S, I'll call it X. Well then, since S is a subset of In plus 1, and In plus 1 is a subset of the positive integers, that implies S is a subset of the positive integers. And since S is a subset of the positive integers, well, that implies X must be a positive integer. But every positive integer is greater than or equal to 1, so X must be greater than or equal to 1. So this shows if X is any element of S, then X is greater than or equal to 1, which is exactly what we wanted. So the second condition would hold as well. So really, this second condition follows from the fact that the smallest positive integer is 1. So that's why we get this. So 1 is indeed the smallest element of S in this case. So this completes the case where 1 is an element of S. Now let's consider the case where 1 is not an element of S. Now the idea in this case is we consider the following set. We consider the set T, which is the set of positive integers x, such that x plus 1 is an element of S. So what this set is essentially doing is, it's taking all the elements of S and subtracting each of them by 1. So since S is a non-empty subset of In plus 1, we should then expect T to be a non-empty subset of In. So to show that T is a subset of In, well, if we consider an arbitrary element of T, called x, well then, by definition, x is a positive integer such that x plus 1 is an element of S. And S is a subset of In plus 1. So that means x plus 1 is an element of In plus 1, which means x plus 1 is less than or equal to n plus 1. So we can cancel out the 1's on both sides, so we're left with x is less than or equal to n. So we have that x is a positive integer such that x is less than or equal to n, which tells us x must be an element of In. So putting this all together, we see if x is any element of T, then x is an element of In, and therefore T is a subset of In. But now we want to show that T is non-empty. Well, that follows from the fact that S is non-empty. Since S is non-empty, well then we can choose some element in S. I'll call it x naught. Now let's note, S is a subset of In plus 1, and In plus 1 is a subset of the positive integers. But since 1 is not an element of S in this case, well then x naught can't be equal to 1. So since x naught is a positive integer, but x naught is not equal to 1, then there should be some positive integer that comes before x naught. So x naught minus 1 is a positive integer. And the idea here is, we're trying to show that x naught minus 1 is an element of T, right? Because T is essentially taking all the elements of S and subtracting them by 1. So since x naught is an element of S, we expect x naught minus 1 to be an element of T. And so to show that, well, by definition of our set T, let's replace x with x naught minus 1. We need to verify that these two conditions hold. Well, we know that x naught minus 1 is a positive integer. That's what we've just shown. So now we want to show that x naught minus 1 plus 1 is an element of S. But that follows, since x naught minus 1 plus 1 is equal to x naught, and x naught is an element of S. So this condition holds too, and therefore x naught minus 1 is an element of T. And therefore T is non-empty. So we see that T is a non-empty subset of In. So by the induction hypothesis, T must have a smallest element. We're going to let m be the smallest element of T. Now since m is the smallest element of T, well then m itself must be an element of T. Which means m is a positive integer and has the property that n plus 1 is an element of S. The claim is that n plus 1 is the smallest element of S. So to show that, well, in that case, we're going to replace m in the definition with m plus 1. So to show that m plus 1 is the smallest element of S, we want to show that m plus 1 is an element of S, and every element of S is greater than or equal to m plus 1. Well, we know that m plus 1 is an element of S. That's what we have here. So all that's left to verify is that every element of S is greater than or equal to m plus 1. So to prove that, let's give ourselves an arbitrary element of S. I'll call it x. Well then, by the same argument that we gave for x naught, we deduced from the fact that x naught is an element of S that x naught minus 1 is an element of T. So it's going to follow from the fact that x is an element of S that x minus 1 is an element of T. But then, since m is the smallest element of T, it follows that x minus 1 is greater than or equal to m. So then, adding 1 on both sides, we get x is greater than or equal to m plus 1. So this shows if x is any element of S, then x is greater than or equal to m plus 1, which shows that this condition is satisfied. And therefore, m plus 1 is the smallest element of S. So putting this together, we have shown if S is any non-empty subset of In plus 1, then S must have a smallest element. So this completes the induction step. And so at this point, this closes the induction. So by mathematical induction, we have proven for all integers n greater than or equal to 0, every non-empty subset of In has a smallest element. And so we're going to use that to prove that every non-empty subset of positive integers has a smallest element. And so to prove this, let's give ourselves an arbitrary non-empty subset of positive integers. I'll call it S. Well, since S is non-empty, we can choose some element of S. I'll call it N. So what do we see here? Well, N is an element of S, and S is a subset of positive integers. Therefore, N is a positive integer. And of course, N is less than or equal to N. So this tells us that N satisfies the requirements to be an element of IN. So N is an element of IN, and N is an element of S. Therefore, N must belong to the intersection of IN and S. So this tells us that the intersection of IN and S is non-empty, but it's also a subset of IN. So the intersection of IN and S is a non-empty subset of IN. But based on the fact that we just proved by induction, it follows that the intersection of IN and S must have a smallest element. And let's let M be the smallest element of the intersection of IN and S. Now, since M is the smallest element of the intersection of IN and S, we know that M itself is an element of the intersection of IN and S. So we know that M is an element of S, but the claim is that M is the smallest element of S. And to show that, well, by definition, we need M to be an element of S, and we need every element of S to be greater than or equal to M. Well, we know that M is an element of S. That's what this is telling us. So the first condition is already satisfied. All that's left to show is that every element of S is greater than or equal to M. So to show that, let's give ourselves an arbitrary element of S. I'll call it X. From here, the whole goal is to show X is greater than or equal to M. And to show this, we're going to split this up into two cases. Either X is less than or equal to N, or X is greater than N. Let's first consider the case X is less than or equal to N. If X is less than or equal to N, well, what do we see here? We have that X is an element of S, and S is a subset of the positive integers. So X is a positive integer. So X is a positive integer such that X is less than or equal to N. And that tells us X satisfies the requirements to be an element of IN. So X is an element of IN. So X is an element of IN, and X is an element of S. Therefore, X belongs to the intersection of IN and S. But since M is the smallest element of the intersection of IN and S, it follows that X is greater than or equal to M. So that's it. This completes the case X is less than or equal to N. Now let's consider the case X is greater than N. If X is greater than N, well, since M is an element of IN, that means M is less than or equal to N. And we know that N is less than X. So this shows X is greater than or equal to M, and we're done again. So we see in either case, whether we have X less than or equal to N or X greater than N, it follows that X is greater than or equal to M. So this shows if X is any element of S, it follows that X is greater than or equal to M, and so this condition is verified. So that tells us that M is the smallest element of S. And so what this tells us is if S is any non-empty subset of positive integers, well, then it must have a smallest element. And so this completes the proof. And so yeah, that's pretty much it for this video.